Alright, so let's look at Prim's algorithm. This is a greedy algorithm that finds the minimum spanning tree for a weighted undirected graph. And essentially what that means is just finding a subset of all the edges that form a tree where you can connect from every vertex to every other vertex. And the cost of those edges is minimized. So for example, here's a graph. What would be a good criteria for finding the minimum spanning tree? So this is going to be, like I said, a greedy algorithm. So first think of some greedy solutions. Well, if we're trying to minimize the cost of all the edges, you might think, let's just start by taking the edges in order. But that's not going to be quite enough. And we'll see why. Well, one, if I just took these edges in order, you'll find that, this edge over here is not part of the spanning tree. So we have to do a little bit more work than that. Well, we'll just start with what is the minimum spanning tree for this graph. Well, here's the minimum spanning tree. And if you notice, we did take the cheapest edge and we took the second cheapest edge, but we didn't take the third cheapest edge because it would have created a cycle, which sort of invalidates the thought of having a tree. Alright, so how does Prim's work? Let's step through Prim's algorithm. Like Dijkstra's, you give it the graph and you give it a start vertex. We're going to maintain a list of vertices that have already been found, so that are already part of the spanning tree. And we're going to compute the total cost of the minimum spanning tree. And we'll have our actual minimum spanning tree itself. So we're going to keep looping while we haven't found everything. So while not all vertices belong in the minimum spanning tree. And we'll have a loop. We're going to have our min weight and our mid edge. So we're going to say for each vertex in found, we're going to say look at all vertices that it's connected to. So for every vertex connected to V. If it's also not in found, so this is where we would have checked, are we taking this edge or not? Well, this is the part where we make sure that we don't keep an edge. That's going to give us a cycle. If the weight of that edge is less than the min weight, then we're going to hold on to it. So we are, in fact, going to take the cheapest edge, but there are two key parts here. We're only going to take the cheapest edge that's already connected to a vertex that's already been found, so like the start vertex. So even if this blue line is the cheapest edge, we can't take that one yet because it's not connected to the start vertex or the other vertex that's part of the found set yet. So those are the two key points. The two key points. We're not going to create cycles, and we can only look at edges that are connected to vertices we've already found. Okay, so in each iteration, another way to say what Prim's does, in each iteration we extend, so that's the key point, we extend the minimum spanning tree in the cheapest manner possible. So how does this compare to Dijkstra's algorithm? So I'm going to break this video here, and you should think about in between this and the next video how Prim's is different than Dijkstra's.